The next few minutes, I would like to show you how to find the real and complex roots of any polynomial. Our approach would be first to show you the tools that we'll be using, starting off with the Newton Raphson recursion technique, explaining the slope intersection concept, and then how we adapt it to complex numbers. We then will talk about the problems of finding multiple roots, how differentiation will help us solve that problem, and what to do about zero terms in our polynomial. We also talk about dividing and multiplying polynomials, and we will use graphic presentation to show our results. The problems that we found were finding the right seat for the Newton Raphson conversion and the precision of the computer. The Newton Raphson technique basically makes use of the fact that we can approximate the slope at a point in the curve with the equation delta y over delta x equal the derivative. If we then solve that equation and replace x0 with x and y0 with y0, we find that when we find the tangent to a point on our curve and project that tangent to the zero line, we get a new x value, and then find the corresponding point on that curve and continue doing the tangents. And we expect the results to converge to the value where the zero of the curve is. We repeat this process, of course, over and over again. We can see that it appears to converge at the point of intersection on the top curve. However, there are two problems that occur. The first is that if the slope approaches zero near the point of intersection, we're dividing by y prime, which is 0. And that is an indeterminate situation. This happens in the first case because we can't see it because we have two roots the same, 2 and 2. On the second equation, we have that a polynomial doesn't cross, and what we begin to see is as we take the derivative, it begins to bounce here until it hits the center point where the derivative is 0, and it would go up to infinity somewhere. So we can't find a complex root using the traditional Newton Raphson technique unless we look at it with complex numbers. You now take the example where y is equal to x squared plus 4, and we're interested in finding the roots, so we set that to 0. We then use the Newton Raphson technique for it, and we get the following equation. If we put in the starting seed of 1 plus 1/2 I, after 6 reiteration, it converges to the number 2. However, if we put in the seed of 1.0 minus 0.5, it converges to the value of minus 2. Not surprising because the square root of 2 of 4 is plus or minus 2. Thus, we see the starting seed makes a difference. At the peak or valley, the slope is 0, so 1 over 0 is indeterminate. Now we look at the situation of multiple roots, where we would have a problem with the derivative being 0. And you'll notice here the derivative, which is in yellow, crosses right at where we have two roots that are equal. And it appears that we could be able to solve for those roots, but we would find the calculations would tell us otherwise. So what we notice is we take the derivative of the equation, we get a new equation, which if we were to put in the value of 10 or 11, which turns out to be the roots, that we would get the right answer in the original equation. So it turns out that when we take the derivative of this, we get another equation in which the roots are 10, 11, and 10.5. We can see from up here. The 10.5 will not be a solution to the first equation, so that's how we eliminate it. So we'll find one or the other first. And the whole idea is by now going to the derivative function, and then that being our primary function, the double derivative being our derivative function, we can now use the Newton-Raphson technique on that and find our roots. The other thing that is also interesting is that when we substitute x plus 10 for x in our original equation, we get x to the fourth plus 2x cubed plus x squared and two zero coefficients. The more times that that's repeated, the more of these zero coefficients, and that gives us how many times that root is duplicated. We sometimes will have to go to, we usually start as many derivatives as we can until we get, just before we get to a linear equation, because we could have 3, 4, or 5 roots in an equation. Once we get that root, we divide it. In this case, since it occurred twice, we divide it by x minus 10 twice, and we get a new equation, x minus 11 squared. And that is fairly easy to find a root using the same process we did for finding the 10. Okay, if we did not use complex numbers in the recursion form, we can see the intercepts would bounce around without converging, though we could find the real root. We set our seed bigger than 6. So over here, if we started over here with the seed that started this here, we would go here and bounce in. If we hit this point as possible, we would then bounce out somewhere and we would be stuck. Or we could get inside the curve by another bounce and then end up being bounced out again along the curve. So, but if we were to pick a seed inside here, we would get to the real root. We pick a seed close to a peak. The tangent intercept could be in a great distance from the curve. Because the curve is so steep out there, it could take a long time to converge to a solution. We notice here, we show something that is oscillating, which happens with most of our polynomials. So if we were to start at this peak or close to it, or this side, we could end up being way outside of our function. An application for being able to solve equations, we took an example of finding the intersection of two ellipsi. And what we found is that when we worked with these equations, we could then get a linear function for y, and then substitute that back into one of our two equations, and we get the following equation. Now, we can solve fourth-degree equations with a formula, but in this case, we're using our Newton-Raphson technique, and it ends up coming out with 4 roots, which we then put back into this equation, and we get the intersections for these two ellipsi. Another use that we had was to study sine curves. And in this case here, we were using the power series for a sine, and we notice the oscillation for the seventh order, which is a negative term, it's very smooth. But when we get to the ninth order, we add this into our factorial, we notice that it's not quite as symmetrical. So it seems that the seventh order might do a little bit better in terms of be sufficient number of terms to get a solution accurate to a few places. Of course, we'd have to go out to more terms if we wanted to get it more accurate. We're also comparing power series in our cofunctions. In this case here, what we've done is we've taken our regular power series, and what we will notice is that if we compare this to one in which we use our power series or one in which we use multiples of pi, x minus, or 1 minus x over pi, 1 minus x over 2 pi, etc., squared, we find out that we would get multiples of pi as the coefficient. You'll notice here that we got 1, 2, 3, 4, 5, 6 solutions, yet we only see 1, 2, 3, 4, 5. We do see 6 crossings in here. You have a better feel how this Newton-Raphson technique with complex trivials work. We're going to look at a cubic equation. Here we see the equation in yellow in the real plane and the blue in the complex plane for the y value. We're rotating around so you can see the shape. In the middle of those two is the actual thing. Here we're now going through the thing plane by plane, and we notice that the first thing we come to is a complex variable at the minus 2I. Notice the red lines intersect both in the complex and real plane. Now, for root 6, the complex plane is a straight line, and we notice where the two blue lines are is where we get the zero crossing. And then finally we move to plus 2I, and again we will see at the red lines that we get a zero crossing in both the complex and imaginary plane. By using this 3D approach in two different ways, we can get a better idea of what's happening when we are trying to find the roots. The next thing we did is besides our own test cases, we picked a test case that we picked up from a college dissertation, and there were 20 samples in this, and we were able to get we solved all of those equations except for one to to at least 8 or 9 decimal points. There was only the limitations of the precision of the machine in terms of when we were multiplying big numbers that kept us from getting more than that. So if we went to double precision, we would have been able to get it to 15 places. And so we can now go down through this, seeing each of these test cases and see the level of complication. All these test cases turned out to be complex roots in here and multiple roots. When there were multiple roots, notice it. When there were multiple roots, it found 4 1s, it found 3 2s, and it found 2 3s. In this case, it found 3 imaginary numbers and 3 real numbers. And we continue over here. This was a particularly exceptional case because it turns out that as we get to larger and larger powers, that we can get larger and larger coefficients. And as you can see here, this is the 24th power. So I recommend not using this beyond the 20 or 21st power. Over here, there were some cases where we had roots that were very close. We used a technique by eliminating the second order part, which would then act as subtracting. So if we found an average of, say, 100 and subtracted from each of these numbers are all in the order of plus or minus 1. The same thing as we go to this. There's one equation which was left out, which we had 10,000 in there. And when we raise that, as you can see, to the fourth power, 10,000 is to the 20th power. So it was beyond the capability of the machine. But 5,000 worked out fine. Okay, so we were very satisfied with the results we got, put a lot of effort in it, learned a lot from it. The program was able to solve any real or complex polynomial, provided the right seed was used. We found this for a seed of 1 plus 0.5i, we could solve all the test cases in which the coefficients did not exceed the precision of the computer. Our results were accurate from 9 to 15 significant digits, but we would have needed double precision to do better. Seed of 1 plus 1i failed in 2 test cases. The use of 3D graphic tools allowed us to get better insight into the problem. We're able to use it to better understand the power series for the sine function. I'm making the code available for a voluntary donation to Math and Physics Exploration at 1054 Freedom Plains Road, Poughkeepsie, New York, provided you give credit for using the program.